Yes. Thank you very much, Julia, and thank you for the invitation to present a little bit here my research direction and where this comes from and where it actually will go. I'm very happy to be one of the newer members of the EBINet, and I wanted to take this kind of also to introduce myself a little bit and to maybe look where there might be also chances for collaboration in the future. So I'm very happy about everyone who joined, and I'm very happy we are recording this. So also later on, maybe we can find some ground for discussion and potential projects. So I named my talk Electrode Architectures for Bioelectrochemical Energy Systems, because this is mainly where I come from. And I try right now to push it into more applied, more continuous, more scalable energy conversion processes, which mainly is also because of joining Jürgen Kahl's group, of course. And I know this topic is probably quite far away from most other EBINet members, but let's see where maybe we can find a lot of ground for collaboration. So this is why I kind of did this like a little track route. I wanted to introduce myself also to the EBINet a little bit more formally. Who are we? Then a little bit more, who am I? What's my background and research-wise, where am I coming from and where is this headed? Where could this diversify to? And then, of course, this particular collaboration possibilities, with whom can we potentially go further, in which directions, also within the EBINet context. So you all know the chair of energy process engineering, where Jürgen Kahl is the chair holder at FAU, at the Friedrich Alexander University here where we sit in Nuremberg. And he has these classical compartments, these classical subgroups of biomass combustion gasification, then the more modeling simulation of energy systems and energy economy, and then this part of second generation fuels and fuel cells. And now last September, you might remember, because I joined the EBINet much closely after, I joined here with kind of a fourth group, the assistant professor for distributed energy systems, where my focus is largely on biocatalytic energy systems. And you might think now, what are biocatalytic energy systems? In general, we have a lot in common with the second generation fuel and fuel cell systems. So we have electrochemistry, basically, and other kinds of biocatalytic processes. You just hang a bio in front of the catalyst processes here. So a little bit more on me. As I already said, my main research focus is bioelectrocatalysis, meaning we combine biocatalysts, which are, for example, purified enzymes or microorganisms that can facilitate the advantageous redox reaction that we want to, for example, use to generate electricity or to valorize chemicals, for example, from waste. And this is not a topic that is very well explored yet. Mostly bioelectrocatalysis is in the nanobiotechnology and in the bioelectrochemistry, more focused in the medical technology sector and other small portable devices, very niche subjects. But also in the energy transition, it gets more and more obvious that we actually need very small and very many decentral energy conversion systems. And actually biocatalysts can have some decent advantages there. And maybe the most important of them is, with increasing also electrochemical energy conversion solutions, we will need more and more catalysts. And we know mostly, especially for the high temperature systems, and especially also for lower temperature fuel cells and electrolysis cells, we need a lot of precious metal catalysts. And as the fossil fuels, these are actually a limited resource on the planet. Biocatalysts, on the other hand, are completely renewable, which I mean not only in a clean energy sense, but also in unlimited resource. Yes, we can produce as much of it as we want, and the more we will actually have applicable biocatalytic energy conversion systems, the more also the prices for biocatalyst production will go down. And we can apply this in several different directions, as I will show. For example, also for waste valorization, which is particularly interesting for ambient systems, meaning that we can also valorize low temperature waste streams, for example, of carbon dioxide. And we talk about the use of biocatalysts in a circular bioeconomy, meaning that we actually want to use biomass resources and exploit them as much as possible before we actually have to combust them or reintroduce them into the recycles. And their biocatalysts can actually work at several levels. For example, as I already said, for CO2 upgrading or other combinations with organic wastes. Now, I already told you, I come more from the biochemist side, and I've spent the last year working on biofuel cell design and a little bit also on bioelectrosynthesis cell design. And here I actually work a lot with different electrochemical analysis tools in the amperometry, voltammetry, lately also a little bit in the electrochemical impedance spectroscopy, but mostly my focus is on the electrode engineering, meaning finding new concepts to actually make these biocatalyst functionalized electrodes more applicable. And here I actually want to show also today some innovative techniques that we combined nano and microstructure particles on electrode surfaces for optimal biocatalyst immobilization. Little bit what we've been doing in the last few months is also going a little bit into the upscaling and to making bigger processes like bioreactor construction, and then different methanogenesis or acetogenesis processes, meaning upgrading biocatalytically also in continuous process. And we also more as future directions also want to go more into the recycling and to the actually manufacturing of completely biodegradable tools out of completely renewable substances. I will tell you a little bit more about my past stations. I studied in Karlsruhe bioengineering and did my PhD and postdoc at ETH in Zurich before I actually joined here. And what I actually do lately, and I start to like it more and more, is to give biocatalytic crash courses to energy technology students and of our new international course, Clean Energy Processes. And also I have the pleasure to make the Renewable Energies 101 for our first years in the international studies, Clean Energy Processes. But let's see how I actually got towards this energy route, which is quite uncommon when you are in the bioengineering field. So I already said I started in Karlsruhe with the bioengineering. Actually, my focus was their downstream processing in the classical bioprocess technology and heat and mass transfer processes, and actually also some computational fluid dynamics courses. And from there, I actually tried to direct myself a little bit more towards the energy focuses. My first station abroad was actually in New York with BASF, where I did an internship on biomaterials that were stimuli responsive, specifically like magneto or thermo responsive synthesis of different polymers that would actually be used in cell culturing. And shortly after, I had the honor to be a summer intern at the University of Arkansas, where I first time worked with biodiesel, which was quite a sticky but a very educative experience, and I enjoyed it very much. And first that I went more from the applied side to the material side was in my a student project that I did at the IITK at the Indian Institute of Technology in Kanpur in India, where I worked the first time on carbon nanoparticles, which became to be a large component of my research. here, actually, it was on bone replacement materials. So very different kind of biomaterial application. Now, finally, where I got in touch first with the bioelectrochemistry was during my diploma thesis. I will tell you a bit more about it later on at the Hebrew University of Jerusalem in Israel, at the lab of Itamar Bena, where I actually learned the first time that there was something like biofuel cells and didn't let go of me since. It fascinated me that you could actually, just by modifying some enzymes on electrode surfaces, could generate electricity, even though this was very fundamental research for the medical appliances, for example, pacemakers, or self-powered biosensors, environmental sensors, stuff like this. And I took this actually as my PhD project in Zurich, where I said, okay, what is actually holding these systems back to make them more scalable, more productive, more continuous, and more operatable in the long run. And with these concepts I developed here, I applied at FAU in Nuremberg, and I was lucky that actually Jürgen Karl saw that we have quite like a common ground here for collaboration, because I was actually not the first one to work with biocatalysts in the lab. We have this very nice intersection of biological power to X, which I also want to talk today mostly about. So power to X, you all know, it's a major component of the energy transition. We all know we need to electrify. We will have more wind and solar generated electricity, which we need to store somewhere. And right now the way to go, or much leads the way, that we will store a lot in hydrogen via, for example, electrolysis. And here we can operate actually and connect different consumption sectors like heating, power sector and mobility sector, but we have the problem of storage. And one way to actually upgrade the hydrogen and to store large amounts until we get this billion-dollar project of maybe hydrogen pipeline network all over Germany or all over the world, is to convert it further to methane, for example. This has the nice side effect that we can actually bind CO2 as kind of a carrier material, react it with the renewably produced hydrogen, and have methane that we can ideally store in our natural gas grid, which is already existing. And here, a major component is, of course, this carrier material CO2, which naturally should be from renewable sources as well, for example, taken out of the air or from biomass directly, but of course it would also be an option to take it from downstream combustion processes or in this industrial waste streams. And here we of course need to pay attention that this CO2 would actually not get released into the atmosphere later on once we combust the methane again. But let's talk a little bit about these different methanation routes. The most known, that Paul Sabatier actually got 100 years ago the Nobel Prize, is the Sabatier process, where you would actually need a certain chemical catalysts, and you would actually work at elevated temperatures and elevated pressures, and would kind of dissociate the CO2 and hydrogen that you feed in the process and recombine it to methane. Now, this is a very energy intensive procedure where, of course, you can make it more efficient in a way that you also use the waste heat. But there is actually another way to do methanation that is maybe not as well known. It's the biological methanation. And here we do use biocatalysts. It's called anaerobic fermentation process. And this actually, you might know, it's the last step you use, for example, in a biogas plant or a sewage treatment plant, where you would actually produce biogas out of organic wastes. And this last step actually relies on microbial methane formers, so-called methanogens, and they are from the kingdom of archaea. And these archaea are actually able to produce very high purity methane at very low temperatures. There are mesophilic ones that work at body temperature, basically, or also a little bit more efficient thermophilic ones that can operate up to a temperature of 65 or some even higher temperatures. And this has actually some very nice benefits. Of course, first of all, you can use also low temperature CO2 waste streams, but also they can tolerate much higher feed gas impurities, for example, like H2S or other stuff that you could actually, that would actually passivate your catalyst in thermochemical routes. And I can show you a little bit what you maybe know from Jürgen's group. There are actually some very successful government-funded projects going on for this biological methanation, where they basically upgrade, for example, biogas, the CO2 fraction of biogas or of other sources, to even injectable methane by exactly the same reaction route. And you see here, the basic process is a biomethanation reactor, which is nothing else than a bioreactor with a classic fermentation, which works anaerobically. And you feed, for example, hydrogen from an electrolyzer in the system, and, for example, biogas, basically untreated. You can get very high methane concentrations. And this works actually already at very high technology readiness levels. I just want to show you here the Orbit project that actually we managed with several collaboration partners last year to yield such high methane concentrations, far above 90%, that we would get gas grid quality, and it could inject it directly into the gas. So this was actually a 50-liter demonstration reactor that we installed in Ibbenbüren at a power-to-gas site. And here you see now the connection between the biological methanation and what I intend to do, the bioelectrochemical methanation. So here you see we have basically the same process. We also feed CO2 waste streams into the system and convert them to methane. The main difference is that you actually do not need hydrogen. You produce your protons right there in a one-step compartment. This works in an electrochemical cell, where you actually enable a reaction by feeding renewable or any kind of electricity into the system, therefore enabling the redox potential and the overvoltages to actually make a upgrading of CO2 at the cathode here. All you need for that is, in the simplest case, a membrane to separate the anodic and the cathodic reaction, because the cathode is actually very oxygen sensitive, and we have oxygen evolution in the anode compartment. And you need, in the easiest case, water to split at your anode. So basically, it's the electrolysis step and the methanation step in one big electrochemical cell. And this is what classically you would call Electromechanogenesis. This is actually still at quite a low technology readiness level, because you deal still with a lot of overpotentials. So you need to induce a lot more electricity into the system to get the yields that you actually want to have. But this is very promising and actually projects up to 5 times higher methane production rates in the future, if we can handle the different deficiencies we are still dealing with here with. Another really nice outlook, what has already been shown on low technology readiness levels, is even a one compartment system where you could work membraneless, which is particularly interesting for upscaling, because the membrane is usually a large cost factor. And the reason why you could work here without a membrane is that here you don't even split water at the anode, but at much lower overpotentials, you would oxidize other organic matter, for example, from wastewater, where you could oxidize these, and you would actually have an electron flow through the outer electric circuit and an ion flow between the anode and cathode, and you could also produce methane at the cathode. So this is a really interesting concept that is right now getting increased scientific attention and is getting more and more explored. We in our lab actually stand here at the very beginning, but a few weeks ago, actually, my master student Maren Lang had our first successful measurement campaign where we actually could make a one compartment system in a gas-sealed Electromechanogenesis reactor, and we could actually already see some gas production. Now, where I want to lead you a little bit today is our research focus that we will go more towards, and this is the electrodes, the biocatalyst functionalization of the electrodes to get efficient electron transfer and therefore efficient methane production. And here we will go now to the point where do we come from scientifically. Here you can already see I come from the background of enzymatic biofuel cells. So this is basically the reverse process of electricity generation, not electrosynthesis. And the concept looks basically the same. So enzymatic biofuel cell is very straightforward electrochemical cell, which has the same components that we're used to from a fuel cell. We have an anode and a cathode connected through an outer electrical circuit, and each of them, or only one of them, is functionalized with a biocatalyst, which in this case is a redox enzyme. And here you will have a catalyzed oxidation on the anode, where you would have certain types of fuels that this enzyme is specialized towards. You know, this key and lock technology that the enzymes are based on, which makes them extremely selective. And on the cathode, you would, on the other hand, have the reduction of an oxidizer, which would actually, in most cases, be oxygen. The really nice thing about enzymatic fuel cells is that you can usually work without a membrane because of this major benefit that they are so selective, even in highly heterogeneous fuel solutions, that the cathode and the anode would actually reactions would actually not have a lot of cross interference, and you would not lose a lot of cell voltage. So basically, you can use these specific reactions if you can find redox enzymes that do communicate efficiently with the electrode surfaces, and if they catalyze the oxidation and reduction, in particular, in a way that you get sufficient electromotoric force. So the redox potentials need to be sufficiently far from each other to actually give you a driving force and close this circuit by ion migration between the cathode and the anode. This was actually shown already for many different systems and can operate off cell powers up to 1000 microwatts per square centimeters. You can already see we are still quite far away from the best performing chemically catalyzed fuel cells, but for small applications, for example, in biotoxicity relevant environments, this is already very established. For sure, as I will show, we need very specific wiring techniques and organic chemistry, anorganic chemistry to actually wire these enzymes to the surfaces. So what did we identify in the challenges of actually going further with these enzymatic fuel cells, apart from the benefits? We identified here 4 different major construction sites. The first and foremost is the lack of electrical communication between the enzymes and the electrode surfaces. And this is actually quite well researched, but not solved in most cases yet. The problem here is that this key and lock mechanism that the redox enzymes are based on is enabled by this active center being very deeply buried in a large protein shell. And this protein shell actually enables only this selective substrate to enter, but also it makes them kind of insulated electrically. And the most important thing in order to generate electricity with these kind of systems is that you actually have an electrical communication between this redox center and the electrode surface. So basically, you have a typical donor-acceptor interaction, and this is usually blocked for most enzymes. This can be explained by the Marcos theory of electron transfer, saying that actually the electron transfer rate is exponentially dependent on the distance between the donor and the acceptor. And most enzymes are actually up to 10 nanometers thick, and these can have a too large tunneling distance to interfere. So the thermodynamics would enable the redox reaction, but the kinetics would actually make it so slow that nothing would happen in real life. So there were two major strategies, or there are two major strategies that you can overcome this electrical insulation. It's either introducing mediated electron transfer by introducing little molecules that can actually shuttle the electrons between the enzyme and the electrode surface. And there is, for some enzymes, also the direct electron transfer. What would you understand under direct electron transfer? It's actually very few enzymes or genetically modified enzymes that can be made to interact directly or to dock directly on a conductive surface with their active center. For example, the bilirubin oxidase, here abbreviated BOD, or the redox enzyme lacase, have the ability, for example, on carbonaceous nanoelements like carbon nanotubes, different carbon nanoparticles, or self-assembled monolayers, to make a partial unfolding on these nanostructures that would actually get them sufficiently close to have very fast and very effective electron tunneling between the active center and the electrode surface. This is mostly based or hypothesized to be based on different hydrophobic interaction, or the so-called pi-pi stackings or ligations. Now, the sad thing about this very efficient wiring mechanism is that most other enzymes cannot do it. This is mostly true also for the larger oxidation enzymes that we commonly use, for example, for the abundant source in most medical related systems like glucose, which you can find in your blood even, which is usually catalyzed by the enzyme glucose oxidase, which would be so insulating that no matter which stacking material you put underneath would not make the active center flavin adenine dinucleotide, or called FAD, to communicate with the surface. For this, you actually need to develop other mechanisms. There have been many publications in the past to find different techniques to actually make this more efficient and to somehow enable electrical communication. What we developed is actually a very straightforward and cheap method to electrically wire, for example, glucose oxidase to the electrode surface, and this is based on mesoporous carbon nanoparticles. Now, mesoporous carbon nanoparticles can be manufactured in many ways, and they have the huge benefit that you can actually tailor the pore size to whatever you want their function to be. Also, they have very large electrical conductivity, and a major benefit for also the capacitance of any enzymatic biofuel cell is the extremely large surface area. Now, what we did with these different pore sizes, which in our case had an average diameter of 7 nanometers, was that we actually utilized the pores, not as in many cases for the enzyme stabilization itself, but for the incorporation of relay molecules, which means that we would actually introduce mediators inside the pores to shuttle electrons between the active center and the electrode surface. What this would look like would actually be different protocols where we would entrap the redox molecules and then cap the pores by the specific redox enzyme, which then we would cross-link with different procedures and actually yield very integrated, stable nanobiohybrid systems that could actually, for a prolonged matter of time, be used for biocatalysis. Now, in this specific case, what we did was finding mediator molecules known for the specific enzymes that we wanted to utilize, which in this case was the glucose oxidase and fructose dehydrogenase, where we found two different mediators that were very successful to be implemented in the pores. One's ferrocene methanol and two tetratiafulvalene. And both of these actually had the positive characteristic that their redox potential would be very close to the one of glucose oxidase or fructose dehydrogenase specifically, meaning the FAD active center, meaning we didn't lose a lot of electromotoric force. Now, for the cathodic mediation, we had the oxygen reduction catalyzed by the bilirubin oxidase, and we actually used a well-known and well-described in the scientific literature mediator called ABTS. This we characterized then electrochemically, and you can see here just as an impression the different stability measurements that we made, for example, at different scan rates to analyze how the peak currents relate to the different scanning speeds of changing the potential towards the electrode, which means you would actually scan from a low voltage to a high voltage and back and see how reversibly the redox interaction of the molecules on the surface were. You can see also here a leaking study over time, where you could actually see that over the time of 60 minutes here, we would actually initially lose a little bit of mediator molecules, but that after a certain starting time, we had very stable systems for enzymatically stabilized systems that would give us very incorporated designs. One more thing I want to show really quickly regarding the electron transfer interaction is several studies we did with Alexander Trifonov, who is a colleague of mine and a good friend, who would actually show that the incorporation of mesoporous nanoparticles with metallic nanoparticles could yield extremely high electron transfer rates in these kind of hybrid systems that would combine all the benefits of biocatalysis and the metallic nanoparticle catalysis. What he would do is, for the one hand, instead of mediator molecules, have some metal salts incorporated in the pores, and then by enzyme capping and the application of an outside potential, we would actually reduce the metals to little nanoclusters, and this could actually function as either a chemically catalytic hybrid material or as an enzymatic hybrid material. Something even cooler we showed, as I think at least, was the incorporation of platinum salt, which we then showed either electrochemically, like the straightforward approach, would form platinum nanoclusters that would behave catalytically, as you see here in the outside in approach, by just growing nanoparticles randomly and then by chance also wiring into the active center and actually bridging the tunneling barrier. But we could also show that by enzymatic catalysis, we could actually grow the platinum salt in a direct bridge from the FAD towards the conductive surface, here called the inside-out approach. And by this, we could actually see for these systems uncompared performance in terms of electricity outputs. And you can actually see that these really grew directly inside the pores and yielded these hybrid systems in this TEM image, where you can actually see a very narrow pore size distribution. Now, let's get to the second problem that we talked about. And I see that we are already quite forward with the time, so I'll hurry up a bit. This is more relevant to the biofuel cell applications than to the electrosynthesis applications, the loss of chemical energy when you work with enzymatic fuel bioelectrodes. This is actually, the origin lies in the biggest benefit of the enzymes, which is their high selectivity, which means that you have a normal one enzyme per electrode system. You will be very limited in what you can oxidize and what can actually gain you electrons being transferred. And this limits also your sources that can be accessed. Meaning, if you have, for example, different potential fuel sources and you don't have the specific enzyme being able to catalyze it, you would actually not yield any electrons from it. You won't oxidize anything, and you will lose this potential fuel source. Secondly, in heterogeneous fuel solutions, when you had one enzyme but not certain others, you would actually also lose out on certain other potential oxidation sources. Also, you would usually only do a one-step catalysis, which yields you in most oxidation steps maybe 2 electrons per substrate molecule, which means that the oxidized molecule would actually go to waste, even though you could potentially use it further. Now, what we spent a lot of time on is actually developing multi-enzyme electrodes, where we would either work in cascading systems as well as in parallel working systems to contain as much chemically stored energy in the system as possible and convert it to electricity. These are the cascaded system are especially interesting also for electrocatalysis, electrosynthesis, where now we actually use these developed techniques towards cascaded valorization, for example, of CO2. Just as an example here, we mostly work with sugar-based systems, and you can see here that actually we yielded extremely selective and yet very well functioning systems on different sugars. Here shown, for example, for sucrose. And here we would actually yield an electricity generation from sucrose by a specifically working cascade that would yield us a power output when we would incorporate this specific cascade that would have first a conversion of a hydrolysis process of sucrose to fructose and alpha D-glucose, which then the alpha D-glucose would have to go an isomerization with the enzyme mutarotas, which then again could undergo the electronic communication with the electrode and produce 2 electrons each for the electricity generation. And this is just some of the systems we developed from this. For example, for biosensors, where you can see here that we could yield an extremely efficient biosensor detection systems down to picomolar glucose concentrations, which we could show chronoamperometrically, but also cyclovoltammetrically. And you can see here one of the example cascaded systems that would actually work on different fuel sources and also different oxidizer sources with specifically different power output curves and different performances regarding to the biocatalyst performance. Now, the third challenge that we kind of came upon is that usually we have oxygen as an oxidizer in the fuel cell systems. If there's no oxygen, just as in most other fuel cell, like classical fuel cell systems, you won't have any electricity generation. Here we actually developed again a system that would give us a little bit more freedom in what we can operate within. And here again, we used the basic enzyme bilirubin oxidase, which is often chosen due to its high redox potential compared to the anodic oxidation. And we actually implemented another cascaded enzyme, in this case catalase, that would cooperate very well in case there was no oxygen and instead hydrogen peroxide. So we would have a cascaded reaction of hydrogen peroxide with the catalase first, disproportionation to water and oxygen, which would actually locally generate such high oxygen concentrations that we could not only yield very effective oxygen reduction, but we could even operate much more effectively than with a purely oxygen-based system. This you can see also here in the noise within the cyclic voltammograms that we would actually get oxygen bubble formation due to this over concentration in the systems locally towards the cathode, therefore also less interference with the anode. And we could have a purely anaerobic oxidation, or even with both substances available, one of the highest ever reported reduction currents per square centimeters of this cascaded cathodic system. You can see here also the power output curves for these different oxidizer sources, where you again can see if we work anaerobic with an additional hydrogen peroxide source, which is locally introduced towards the cathode, we could actually get up to 250 microwatts per square centimeter. Okay. As maybe the last challenge in this topic is and this is still a major issue, is the operating lifetimes that are still very limited on the enzymatic fuel cell systems. And here we also made actually several studies to increase the operational lifetimes, which are low due to many reasons, mostly because sometimes after long operating times, the biofouling can occur, which is also a problem sometimes for microbial systems. Then we mainly have in very sterile environments still some contaminations of macrophages, which would just digest the enzymes, meaning our biocatalysts, or we just had clogging of products in high heterogeneous solutions, or simply disintegration. You know that we have these chains of amino acids, these polypeptide constructs of enzymes, and they are actually denaturating quite quickly. So this is like the major disadvantage of enzymatic systems, that you cannot really make them long lasting. There have been a lot of advances, for example, with including them in pores or in hydrogels or other stabilizing systems. So your systems can maybe last up to a few months, but still you have this major insecurity of having for having a continuous process. Now, certain things that we developed, for example, incorporated magnetic nanoparticles that we could protect the electrodes with. We also developed some systems that we could react to different fuel sources available by immobilizing different additional enzymes on magnetic nanoparticles, which then by an external magnetic field, we could introduce onto the electrode surface, and therefore also oxidize other substrates available by cascadic reactions. And we developed kind of a bypass mechanism with a biofuel cell completely being able to react to deteriorating performance of the biocatalysts by using them on magnetic nanoparticles and being able to recharge the systems by replacing the biocatalyst even under operation, which you can see here in a long record of the power output of this biofuel cell based on fructose dehydrogenase and bilirubin oxidase, which could actually always be completely re-energized when it dropped under a cutoff voltage of 40 microwatts per square centimeter. So maybe for this part, we will stop for now. I don't know, Julia, maybe I will stop after this intermediate conclusion. We actually showed in the work with these enzymatic fuel cells that we do get very highly performing enzymatic electricity generation, which is extremely selective and very fast, but still limited to very short operational times. It can work in heterogeneous fuel mixtures, which is particularly interesting for medical engineering or also small disposable, portable or implantable devices, but we still have a major issue with the runtimes of these devices. We could actually show a much higher applicability with these different nanostructure and carbon supports, which go very high promise also for other bioelectrochemical energy conversion processes. And we could actually show decreased voltage losses, increased electron transport rates, and increased stability with these techniques we developed. Now, we want to use this knowledge we gained through the work with enzymatic fuel cells to actually work in an electricity-enhanced biocatalysis. And here we now draw our conclusions of the knowledge we gained already towards the bioelectrochemical power to gas sector. here we want to particularly focus on efficient tailoring of the size of the biocatalyst to the available pore sizes of tunable carbon electrode support. And we also can rely on very good performance of, for example, carbon metallic hybrid structures or also magnetically responsive nanostructures. And now I have many more slides. I talked much more than I thought. Julia, what do you think? Shall I continue?
So it's 10 to 11. How much longer do you think it will go?
As long as you want.
I mean, we have until 11:15. Why don't we quickly break here and see what people's responses are, because we want to have time for discussion, right?
Yes. And maybe someone has already questions they can ask now. And otherwise
maybe we should stop for that and then go into word 2, no?
Yeah, otherwise I'll just talk as long as you like.
Yeah, let's open the floor. Maybe just unmute yourself and raise any questions you have at this stage.
I can jump in. It's Jewel here.
Hi, Jewel.
Hi, this is really exciting and very comprehensive in terms of the different applications and things like that. I guess what I'm interested in is in that CO2 conversion space. And so you talked about that a little bit when it came to the biogas, but maybe you could elaborate a little bit more on the conversion of CO2 using some of these devices.
Yeah, actually, yeah, what I showed now in the last slides was for electricity generation, which means you need higher energy content of the fuels that you oxidize. When you do this reverse, which I will actually show now in the next slides, you can actually valorize like a low energy substance and make it, for example, into methanol or into formaldehyde, or into, even when you have a little bit more complex processes and maybe some fermentation processes, you could make, for example, biodiesel out of it, or certain other electricity enhanced fuels, let's say. And this actually works because of this very specific catalytic processes. You have these dehydrogenases, these enzymes, that are actually working on a cofactor called NADH, and they can also electrically communicate with electrode surfaces. So basically, to upgrade CO2, you could use electrons that you get from an outer electric circuit. So basically, you could wire a wind turbine when the grid is full, let's say, and you have excess electricity. You could just wire it to an electrosynthesis cell, for example, a bioelectrosynthesis cell, and make, for example, methanol with a enzymatic cascade. Does that make sense?
Great. Yeah, definitely. And I spent more time on the straightforward electrochemical processes. Are there sort of trade-offs associated with doing this from a bio perspective? Are there some advantages and disadvantages that you'd see?
I think the major, there are several disadvantages for sure. You have always higher timely yields with purely catalytic systems, like chemically catalytic systems. With the bioelectrosynthesis or purely biological catalyzed systems, you have the large advantages of higher tolerance, like towards impurities. You can use waste streams basically before, without any pre-processing steps. You don't need to purify it in advance. Then you could also utilize low temperature, like even room temperature CO2 exhausts, which so many industrial processes have when they actually just blast it in the atmosphere. You don't need to heat it up to have a thermochemical electrosynthesis route. You can just use it as is. And major advantage, really, if we can solve all the other problems that are still associated with it, is this high selectivity. Usually in CO2 electrosynthesis, you have a few catalysts that can, for example, make formate out of CO2, right? But you always get a broad selection of what your products are on your catalyst surfaces, right? So in bioelectrosynthesis, you actually get only one product and only this one. And if you have enough time, if you give it enough time, you can actually get very, very high purity e-fuel streams if you want. But this is still very at the beginning. There's a lot of problems to solve first.
Yeah, but I agree that the selectivity is an issue. And what we find from a life cycle perspective is that the separation energy is non-trivial and can actually sink the pathway in terms of the energy balance. And a lot of folks developing this are not incorporating that into a lot of the estimates that they're making. And so selectivity would be a great benefit if you could do that more precisely. Great. Okay. I already see potential connections, and I'll follow up with you afterwards for sure. Thanks.
Yeah, I was actually also hoping that you could maybe in the future help me a bit on this very in the beginning life cycle assessment and techno-economical evaluations, because yeah, I hear from other chemists, electrochemists, that you can make millions if you make like a catalytic process only 0.01% more selective. Yes, because the purification costs are so high. So still a long way to go, but there's for sure a lot of potential.
Okay, thanks, Jules and Katharina. Bernhard has his hand up.
Yeah, Katharina, nice presentation. I'm especially intrigued by your biological fuel cell, which makes methane, because it looks identical to what happens in groundwater, just over much slower rates and longer time periods, takes hundreds to thousands of years. So you probably mentioned that, but I didn't catch it. How pure is the gas with methane which you take out of your fuel cell? And what's the limiting factor? Can these archaea keep producing forever, or are they running out of energy at some point and your production goes down?
Basically, that's the nice advantage of using archaea over purified enzymes. They can reproduce, right? Problem is they still need some nutrients. They still need some other minerals and stuff. So you don't only have what I showed, this input of water and CO2, for example, or like organic waste. They need certain other sources too. But then, yes, potentially they are immortal. Yes, okay. That's something really nice. And also potentially slower conversion rates. Yes, electricity enhanced, we could actually speed it up a lot. There's not enough reliable data yet to actually show this reliably and comparably, but we aim and we think that we can aim towards 100% methane purity. Right. Yeah, this is maybe not 100.00, but you could actually enhance it over a catalytic process where you maybe have optimally 70 to 85% methane after typical methanation process. With the biological methanation, you can already get far up above 90%. And electricity enhanced with the systems that we hope to improve further, we can basically catch hopefully every single CO2 or organic substance to upgrade it.
The key will be to keep oxygen out, right?
There's several keys that we need to do. Actually, Jürgen maybe can say something about our methanogenic archaea that we are currently using in the lab, which don't seem to be that oxygen sensitive. From what I know, this is a major issue, and the over potentials. Actually, you need to find a system that will really give you methane and not split something else. Like you need to find the right over potential to apply. And you, of course, want also high Faradaic efficiencies, right? You don't want to waste all your excess electricity. And in the end, you have pure methane, but you actually invested insanely much electricity. So right now, it's not the ratio of power to chemically stored energy is not super good. Yeah.
Thanks.
Jürgen, you have your hand.
Yeah, thank you, Katharina. Well, it's still quite new stuff for us all in Nuremberg. Even so, I understand that oxidation of the glucose, it's pretty much state of the art, or that's what you did already in Israel. Yes. And so, and what is the status actually for the reduction of the CO2? Is that also shown in lab scale, or is it, did you do it already, or is it something you're planning to achieve?
Enzymatically, there's a few papers on it that show success, and we are actually doing it right now in this moment. One master student is actually doing the first step, where he wants to electrically enhance the reduction of CO2 to formate. And we already see a little bit happening, and it works quite well, but we need to incorporate the mediators and so on. We will make it much more efficient. It was shown before that this actually works. Now, microbially, this works very well already in lab scale. Also, this is electricity enhanced. The cascade from CO2 to methanol, purely enzymatic, that's actually very well documented for different systems. And for example, also in ionic liquids and these different reactions. That's something quite established, but also not upscaled yet. Like, yeah, all enzymatic systems are basically in the lab scale, maybe 5 milliliters. And yeah, there's nothing where you talk yet about operational lifetimes.
Okay, and to get from CO2 to methane, for instance, how many enzymes do you need? It's a cascade of several enzymes that you.
Actually, CO2 to methane, I don't think there's a direct enzymatic way, or at least not a very efficient one. There you would go microbially. There you have this, that are very complex metabolic processes, right? Which are great for us because they basically give you their waste, the methane, which is for us very valuable. But yeah, there's no straightforward way to do it enzymatically, as far as I know.
Maybe short last question. So I do not remember exactly, but it was at University of Calgary where there is one group in Alberta working also on these biofuels. That was in Calgary, I guess, or I do not know whether Jule knows the group. Do you remember the names?
I think his name was Professor Dhar, D-H-A-R, and he would actually couple anaerobic digestion processes to this electricity enhanced methane production. So that's what you commonly do in this in this one compartment, right? Now, wait. So anaerobic digestion, meaning biogas plant, that you would actually couple the organic waste oxidation with like enhanced electricity input to increase the methane production. And I have to look it up. I think it's D-H-A-R. I forgot the first name. Professor that works on that there, yes. Also microbially.
Okay, thank you.
Okay, well, so Katharina, we have a few minutes. Do you want to continue? Like, we have 15 minutes, so maybe you want to take another 5 or so to speak a bit more, or how would you like
actually, I can wrap it up a bit, and that will be fine. Actually,
yeah,
good. So, where to? So we come from this enzymatic biofuel cell research, where we would work on different cell designs and this 3D carbonaceous electrode architectures, where we want to, in the future, as I already say, work more on biodegradable systems and also recycling of otherwise discardable materials. For example, to research new renewable and recycled electrode materials. Then here, I particularly want to know how good my system would have to perform, projecting if the enzyme production costs would go down, for example, and we could cost efficiently replace our electrode, our biocatalytic material as often as we want, how good they would actually have to perform to be competitive with like a decent chemically catalyzed biofuel cell. Just yeah, that's one of my goals, just to get an understanding. And Then we, of course, also work in different collaborations with different material designs and their electrochemical collaboration. There are different master theses going on already, and we are actually approaching nicely in this renewable carbon direction as electrode support. Then what's also very new for me, what we're currently trying to explore more, which I already talked about, is using enzymatic cascades also for the opposite direction, so for CO2 to value-added chemicals. And here actually a very interesting way to go is with the collaboration of a different institute here in Erlangen, where we would actually apply the enzymes in an ionic liquid phase on carrier materials, that we could have a very high CO2 dissolving in this ionic liquid phase for the catalytic interaction, and then that we could projectively even operate enzymatic catalysis at a gas phase, for example, of a CO2 stream. Also here we are actually making quite good progress, as I already said. Then another little bit off the route we are also going after is long-term to do enzymatic recycling, especially of stuff that is by now only combustible by incarceration. And that's actually finding routes to biocatalytically split or upgrade cellulose or super absorbers that we, for example, know from baby diapers. Now, our intersection with the chair of energy process engineering of Jürgen is me moving more from the purified enzymatic catalysts to the whole cell systems, meaning the microbial systems. Here, of course, we already have a lot of collaborations in different projects. For example, with Thomas Trabold, who is working on this very prestigious multi-culti project with the leading microbiologist, I want to say, in Germany, where we built a very innovative bioreactor to actually cultivate most microorganisms that are not yet cultivatable. Then Lukas Schindhelm, who is also here today, is actually working on a really interesting process of integrating a trickle bed reactor for biomethanation with pressurized water scrubbing, meaning already dissolved carbon dioxide from, for example, a biogas process. And we want to move this, as I already introduced, more into the electromechanogenesis, meaning biomethanation plus external electricity. And here we had this first very nice master's thesis where we got first nice results, and we actually want to take this further into reactor design. You can imagine that compared to a simple stir tank reactor or a trickle bed reactor, where you can actually have a very good understanding of where your dead spaces might be or where your streaming limitations might be, you have to incorporate here the two electrodes, which are usually two-dimensional, into a three-dimensional reactor. So you, from the beginning, have a lot of inefficiencies, which we want by modeling and by lab scale designs that we actually want to upscale to make much more efficient in the geometries and also in the different electrode structure designs and demonstrations, that we can actually fit them much better into innovative reactor geometries. Then, of course, also here we'll go into the electrode engineering. And as you can see, this is what I was talking about with the different knowledge transfers from what we can actually know from the previous systems that will also apply to the microbial systems, even though, of course, we talk of completely different size scales here. Enzymes, we talk about a few nanometers. Microbial systems, we talk about up to a few micrometers for one cell. So we'll need to adjust our nanostructured electrode surfaces to maybe microstructured devices that will fulfill their purposes optimally to immobilize and stabilize and enhance electron transfer between the microorganisms and the conductive electrode surface. So here, a large thing, as I already said, will be new architecture development, new material development, for example, from sustainable carbon sources. And of course, we have a lot of interaction and knowledge transfer also from the larger energy processes regarding pressure vessels, gas analysis, automation, certification, where we really have many professionals here, and also the large, abundantly available knowledge in our chair on CFD modeling, which we want to use to find innovative geometries. And here again, now this I can skip because I already said basic, only difference between a biofuel cell and bioelectrosynthesis cell is getting electricity out or putting electricity in, but we use basically the same technologies to wire the biocatalysts to the surfaces. Now, with who? Actually, I also can cut this a little bit short. We are now performing these first experiments on the funding, initial funding of FAU with the Emerging Talents Initiative, where we actually want to build a parallel mini reactor compartment where we can test electrodes in a very reproducible and controlled reaction parameter environment by making 8 of these mini one compartment reactors connected to each other, and that we can electrochemically and biologically analyze them. We want to do this for the one compartment, but we actually in the next months also want to do it for the H cells, meaning for the 2 compartment systems that are connected through a membrane in between. Yeah, as I already said, the major focus will be electrode materials, the structure, and then the scale-up strategies and novel geometries, different modes of operation. Maybe I can skip this one because I already said all of this, and these are basically the major goals that we are working towards. Of course, we want to increase methane production and decrease over potentials because, as I already said, we don't want to waste our electricity that we feed into the system. We want to get to the most electrons possible actually getting stored into methane. And also here we want to increase the stability. How different routes where we will go will actually majorly depend on the microbial cultures that we will implement on the electrode. We can work planktonic or with biofilm enhancement on the electrodes, that we actually get very beneficial interactions between the microbial cultures when we work with a mixed culture, for example, that they will have different metabolisms stabilizing each other. And we can, there's actually some preliminary studies in literature that state that depending on the different interactions that we have from the different microorganisms, that we have different techniques of enhancing the products that we want to achieve. Meaning we can also with microbial systems either have mediated electron transfer or direct electron transfer, meaning sometimes we have the protons forming on the electrons, sometimes we have different carbon sources on the electrodes, which all depends where we actually get our electron donors and electron acceptors from, and where on the electrode it takes place, or if it actually takes place in the electrolyte. And all of this, when we know more about our system, or when we design our system specifically, we can enhance certain specifications that we want to see. For example, by working on the conductivity of the materials, of course, increasing the surface area, but for example, also on increasing the hydrophilicity or doping the surface with certain nanomaterials or positive surface charges to, for example, slow down one organism and enhance the metabolism of another, or even to tweak by the microstructure and by the microenvironments on the electrodes the metabolic routes one microbial culture would choose. And also we will majorly work on biocompatibility, of course, to for the biofilm formatting systems get increased performance by getting very stable systems. And as I already said, this for the electrode development, we are still at a very low technology readiness level. So we try to develop superior electrode designs in the next year or so towards technology readiness level of 3 or 4. And for existing carbon electrodes, for example, which are mostly used like these different felts or these graphite brushes that are usually used, we want to actually bring them from already performing and already demonstrated on the lab scale to scalable electrode geometries. And there are several challenges, as I already said, associated with it, where we come upon very different problems if we talk about the one compartment or the two compartment configuration. For the one compartment, actually, as I already said, we can work, for example, also with organic waste streams, for example, in a wastewater treatment plant, where of course we have the electrodes exposed to potentially very viscous and non-homogeneous feedstocks, which might decrease their performance significantly. And also, as Bernard already mentioned, also we can have the digestive state actually poisoning our electrodes by producing oxygen when oxidizing also. Also, as I already said, low electrode surface to volume ratio, which is something I think we can fix. Then for the two compartment configuration, we have on the anode water splitting, where actually we face exactly the same problems as in normal electrolyzers, which is mostly we need very precious metal and very high quality anodes for the water splitting, which is a major cost factor. And again, we need to work on the cathode, on the biofilm formation, and potentially also on incorporating biocatalysts on the anodic reaction. Then, as I already mentioned, the membrane is a major cost factor. And in the two compartment, when you work with water as the proton source, you need a membrane. You don't get around it. And there's actually a lot of research going on also in developing alternative materials, for example, to the commonly used Nafion membrane. Now, in general, for the two compartment, we come towards what has been shown in the literature towards scale up, that we get very, very low outputs, and we actually, what has been shown in the past, still invest more electricity and then we get out in potential methane stored energy. All right, so we will develop different.
Katharina, we're at 11:18. I just wanted to remind you, we're 3 minutes already over. The PI meet has to start very, very shortly. So I just want to see if you can maybe try and
I can, because
conclude.
No, we'll work on fluid dynamics. We'll work on thermodynamics, obviously. And that's the last slide. So,
okay, very good.
Maybe
sorry, Katharina, but yeah.
No, that's fine. I knew I can talk too much. So that's basically everything again. And here, really, I would look forward to collaborations on entry-level techno-economical analysis and LCA analysis. And a major thing really needed in this field is reliable data sets to actually build upon with scale-up strategies. And here I just put some further reading of who's interested and some of the already running projects on the biomethanation, for example, which hopefully will sometime soon also have some electromechanogenesis funded projects to add. And that's it. Thank you, guys.